Okay, our second video covers question 4 and question 5, and probably no more, but I'll see what it looks like when I get to the end as far as time goes. So question 4 involves average cost per unit. And so we're given a cost function of after n years of use of 2,400 plus 100 times n plus 20 times n squared. And we're asked to first simplify the average cost function. Well, the average cost function is just the cost function right here, same as here, in the numerator divided by the number of years n in the denominator. Well, to simplify that, you want to split this up into 3 separate fractions. So the first term, 2400, is then placed over n, and 100n is placed by itself over n, and 20n squared is placed by itself over n. And in the middle fraction, the n's cancel multiplicatively, so we're left with 100. And in the 20n squared over n, one of these n's, because remember this is n times n, one of those n's cancels with the denominator multiplicatively, and so we end up with 20 times n. So this is the average cost function requested in part A. Then in part B, we are asked to evaluate the average cost at certain production, or after a certain number of years. So after 5 years, our average cost per unit is given as 680. Plug 5 into n here and here, and you'll come up with 680. At 10 years, the average cost is 540. At 12 years, the average cost is 540. And then at 15 years, it's 560. At 20 years, it's 620. And at 11 years, it's 538.18. Now, we were only asked to evaluate at 5, 10, 12, and 15 years, but after we do and plot those on the graph, we'll see that the function is decreasing to a certain point, and then it looks like it's increasing again, and so I threw 20n, even though it wasn't requested in the question. I threw 20n to confirm that for myself. And then it says that we're to use the graph to inform our choices. In other words, to decide what other average cost calculations would be useful to us to estimate the age, the number of years at which the average annual cost reaches a minimum. Well, we can see that with a point here and a point here and a point here, and especially with a point here, it looks like the function probably bottoms out somewhere in this area. And so we have the value at 10 years and 12 years, and so we say, well, let's check what it would be at 11 years. At 11 years, that average cost is $538.18, which is ever so slightly lower than 540. And as we did in class the other night, if we want to check what happens at 10 and a half years and 11 and a half years, we can. But 11 is a pretty good estimate. It looks like the function bottoms out at about there. So it appears that the age of 11 years is the age at which annual cost is at a minimum. I don't need you to be any more precise than that on the exam. There should be a very obvious point like that that'll give us a reasonable estimate. And so the answer to the last part we kind of already answered by making these calculations here. The the minimum average annual cost is $538.18, and we estimate that to be at 11 years. Now, question 5 asks us to graph an exponential function. Actually, it asks us to graph 2. And this is exactly like what we did in class when we graphed 2 to the x and 1/2 to the x, except for this practice it's 4 to the x and 1/4 to the x. And so using x is -2, we calculate that when x is -2, 4 to the x is 1/16, which is approximately 0.063. And when x is -1, that's the reciprocal of 4, which is 1/4, which is 0.25. When x is 0, 4 to the 0, because remember, the x is in the exponent here. So we raise our base 4 to this value. And 4 to the 0 is 1, because anything raised to the 0 power is 1. And of course 4 raised to the first power, 4 to the 1 is 4. And 4 squared, 4 to the second power, 4 squared is 16. So those are our function values. Now, the other function we're asked to graph is the reciprocal of this, and all these values are going to be the same, except they're going to be flipped, sort of vertically. So whatever was up here is going to be down here, and whatever was down here is going to be up here. So 1/4 to the -2 is going to be the same as 4 to the +2, or 16. 1/4 to the -1 is going to be the same as 4 to the +1, which is 4. And of course anything raised to the 0 power is 1. 1/4 to the first is going to be 1/4, which is 0.25. And 1/4 squared is going to be 1 squared over 4 squared, which is 1 over 16, which is that 0.063 value that we saw over here. And when we plot those points, and I forgot to mention that it says here that we can only reasonably fit the graph over a domain of -2 to 2. So then we see that when x is -2, then x is 0.063 for the 4 to the x, and etc., etc. And of course when x is 2, then y is 16. Our function value is 16. And so just like we did in class with 2 to the x and 1/2 to the x, we have an increasing function for the base that's greater than 1, and we have a decreasing function for the base which is in between 0 and 1. And it increases and decreases at a much more rapid pace than the 2 to the x and 1/2 to the x, but the graph looks very similar. It looks almost exactly the same, as a matter of fact, because you can see what I did is I changed the scale of the x-axis here. I expanded it, I stretched it out, so these values are more reasonably plotted here, and our function then is easier to sketch. The question on the exam will be, it'll be the same. I'll do the same kind of thing, where I will scale the graph appropriately for whatever functions I ask you to graph. And I'm going to stop this recording, stop this video here, because the next questions are all similar, and they are dissimilar to this question.